Hello, everyone. Welcome to my session today. My topic is a deep dive into EOF and its impact on program analysis. And what is EOF? What is EOF? EOF stands for Ethereum Object Format. And in today's session, I will demonstrate how our tools and EOF facilitate and help with static analyzer in control flow analysis. And before we dive deep into the topic, please let me first introduce myself. My name is Luis from Amber Group. I'm currently the Web3 security research intern. In Amber Group, I contribute to Mosra, a Ghidra-based EVM decompiler developed by our team. And here is today's agenda. First, we will begin with a brief introduction to Fusaka upgrade and EOF upgrade. Then, we will take a look at the current limitations of legacy EVM contracts and the Ethereum virtual machine architecture, especially the challenges we faced during program analysis. Then I will highlight the key features of Ethereum object format and how the EOF help with program analysis and control flow analysis. Then I will come back to Mosra and demonstrate how we integrate EOF into our tools. EOF, it is not a standalone upgrade. It is part of the Fusaka upgrade. The Fusaka upgrade is the upgrade after the Pectrops upgrade. Fusaka upgrade introduces significant changes in Ethereum's execution layer, especially the Ethereum virtual machine part. If you want to know more details about Fusaka upgrade and the Ethereum object format, you could take a look at the following two EIPs. And what is the current, what problem does EOF try to solve? The first one is the stack to deep issue. Although it is not a problem for the Viper compiler, but it is a long-standing issue for the Solidity compiler. When we want to pass data across functions, first we need to pass the data onto the stack. And we could access it later using swap or dupe operation. But in legacy EVM opcode, it only supports access up to 16th stack position. This limited range could be easily exceeded for complex function and nested logics. However, in EOF, EIP 663 is introduced, and 3 new opcodes are created. They are swap-in, dupe-in, and exchange. Allowing for the first 2 opcodes, they are extended version for dupe and swap operation, allowing access up to 256 levels deep. For the exchange opcode, you could provide an immediate value and specify which 2 stack position should be swapped. So this solved the previous limitation in the stack management issue. And the other issue is there is code deployment validation issue. Currently, we could deploy undefined or invalid bytecode on Ethereum network. However, this is impossible after EOF is activated because several validation rules are introduced in EOF. all the bytecode deployed will be validated during the deployment time. And all the immediate values should be properly provided as well. And there are more validation rules. And finally, it is the legacy EVM has an undefined structure. But in EOF, a versioning header will be introduced, and there will be a well-defined layout for the EOF compatible bytecode. We have talked a lot about the changes in EOF. However, this is not our focus today. Today, we will be concentrated on program analysis part and how EOF help with program analysis. So what do we want when performing the program analysis? When we perform the program analysis, first, we want to segment the bytecode into functions. And then, to segment the bytecode into functions, that is to detect the function boundaries. And then we could decode key parameters. For example, the input arguments or output arguments for these functions. And then we want to know how one function interacts with one another. To achieve this goal, we need to detect several patterns. First, we need to detect the code patterns, and then we need to detect the return pattern. The branch pattern is also important in control flow analysis, but we will talk it later. We will discuss it later. And in legacy EVM, it only supports dynamic jumps. So it only uses jump to represent both code and return pattern. That makes it difficult for static analyzer to distinguish whether a jump represents the code pattern or the return pattern. And in Mosra, we create an analyzer to distinguish these patterns. First, and this is how it works. First, when we encounter a jump operation, we will check its preceding operation. If the preceding operation is a push operation, we will classify it as a code. However, if the preceding operation is pop, swap, or jump test, we will classify it as a return. So now we are able to decode the code and return pattern. But that is not enough. We want to further decode the return address and the number of input arguments for these functions. And we built another analyzer for analyzing this data. For the return address, we first locate the basic blocks that contains the code pattern. You can see there is a jump with a preceding push. So this is a code pattern. And the return address is usually the program counter after the code pattern. So this 5C is the return address. And this program counter is pushed before the code pattern. So you could see a push operation in the same basic blocks. And how do we decode the input argument numbers? The algorithm is we could simply analyze the state change between the push operation and the code pattern. There will be some additional rule to handle the edge case, but we will skip the details here. So by analyzing this green section here for the state change, we could derive the input argument numbers. However, what could we decode the output argument numbers? To be honest, we do not know the answer. And this is the simple workflow like we mentioned earlier. Here we can see a call pattern and a return pattern. And there is a push operation that push the return address. And this purple section is where we decode the input argument numbers. But this is not always straightforward because we could not decode the input argument numbers without executing the bytecode sequence. But sometimes it becomes complex, like this one. And this is how EOF simplify the control flow analysis or the program analysis. Here, we will come back to EOF introduction and show you how it improves program analysis. This is a simple counter contract, and I compile this contract using the legacy EVM compiler. And I pass it into Mozilla. And here is the display result for Mozilla's listing view. As you can see, in the legacy EVM contract, there is no specific format for the bytecode. And all the contract logic starts at offset 0. However, this is different in Ethereum object format. In EOF, everything is organized as a container. And in a container, there is a header part and a body part. In the header part, in EOF, it introduced different kind. We have the type kind, we have the code kind, the container kind, and the data kind. And the header stores important metadata for each kind, like its size, while its actual content, the value associated with its logic or data, is stored in the body part. And this is the visualization of the EOF contract layout. First, we will have the header part, as we described earlier, and then we have the body part. And at the beginning of the header part, we have a magic value to distinguish whether this bytecode is EOF compatible or it is from legacy EVM contract. And the value is EF00. And just to clarify, EF here represents executable format, not Ethereum foundation. All right. And there is a following 1 byte number that represents the version. And the following section is the metadata for each kind. First, we have the type kind. The type kind contains important information for each code section. However, we will discuss it later. Next, we have the code kind. Each code section here would represent one function in EOF bytecode. And after the code kind, here is the total number of code section. And here is the list of the size for each code section. And then we have the container type. It is interesting that an EOF compatible bytecode itself is a container. But here we could have nested container. However, it is not a most. You could have 0 nested container, or you could have multiple nested container inside one container. And finally, we have the data kind. In EOF, the code data separation pattern is introduced. The contract logic is stored in the code section, while the data, like the constant or immutable value stored in smart contract is placed in the data section. And there is a terminator that separates the header section and the body section. If you want to visualize the EOF bytecode layout by your own, you can use this website, EOF.WTF. You could pass your bytecode in the website, and it will decode the metadata in the header section and decode each section for you. If you are using Foundry as your testing framework, you could add this flag to compile your contract with the EOF compatible compiler. And then you can pass the bytecode generate to this cast cheat code. And then the format will display directly in your terminal, like the following result. All right, we have a brief introduction to Ethereum object format, but how these changes help with program analysis? Like we have discussed before, in program analysis, the first goal for us is to decode the function boundary. In EOF, we have the code section, and each code section represents one function. So now we no longer have to decode the function boundary. And then in EOF, a new opcode is introduced. It is the CoF opcode. The CoF opcode would represent the code pattern. So now we have the code pattern. And there's also some semantic changes during execution. Now, for each code section, it has its own program counter scope. So the program counter would reset to 0 at the beginning of each code section. And a new component, the return stack, is introduced. When we perform the CoF operation, these two items are pushed onto the return stack. The first one is the code section index. And the next one is the program counter after the CoF operation. They are combined together and pushed onto the return stack. And what about the return pattern? Another operation, returnF, is introduced. In returnF, one item will be popped from the return stack, and the current it will return to the code section specified and the program counter that is provided in the previous CoF operation. And what about those non-returning functions? For non-returning functions, we have jumpF, and it is defined in a separate EIP. For jumpF, it will not push any items onto the return stack. That means when it jumps to the target code section, it will not return. And we already have the code pattern and the return pattern. Then how do we detect the input argument or the output argument? We have mentioned in EOF header, there is a type kind. In the type kind, each entry consisting of 4 bytes. It contains the input argument number and the output argument numbers, as well as an information for the max stake height. So here, we could directly read this information from the type section. Do you remember how we decode this value in the legacy EVM contract, it is so complex, but now it becomes very easy. So here is a quick summary. In program analysis, we want to detect the function boundary. And we also want to detect code pattern and the return pattern. And now, the code section, each code section would represent one function. And the code F and jump F would represent the code pattern. And the return F would represent the return pattern. And we also mentioned the branch pattern is important as well in control flow analysis. In the legacy EVM contract, we also use dynamic jumps for the branch pattern. We use jump I, but in EOF compatible bytecode, we use list 3 opcodes. For list 3 opcodes, you should provide an immediate to specify the offset you will jump to. So it will be more easier for static analyzer to extract the value from the bytecode. And it would help us combine these together. It will help us reconstruct a more concise control flow graph, and the process will be simplified significantly. And finally, we no longer need the dynamic jumps. So the following 3 operations, jump, jump I, and jump dest, is duplicate in EOF. And that is also a good news for the Ethereum client, because they no longer need to validate the jump dest during the runtime. And then we will come back to Mosra and show you how we integrate EOF into our tool. Let me first briefly introduce Mosra. Mosra, it is a Ghidra-based EVM decompiler. Ghidra is a very popular Web2 decompiler, and you could build extension on top of Ghidra. Ghidra supports multiple architectures. For example, x86 or ARM and more architectures. But it does not natively support EVM. So, however, it has some powerful features like the control flow graph reconstruction and like the compiler features. So we built Mosra and support the 256 bits for the EVM compatibility. And we also built multiple analyzers to perform program analysis. And this is the workflow for program analysis in Mosra. First, we will compile the contract into bytecode, or you can fetch it on EtherScan or anywhere else and pass it into our custom loader, which perform pre-processing for the content. And then the data will be passed to different analyzers. We have the function analyzers that detect different patterns. And we have the input arguments analyzers that perform the algorithm that will extract the input arguments number. And we also have this disassemble analyzers. We define the state definition for each bytecode. So this disassemble analyzer will convert the opcode to intermediate representation using this definition and help us display the decompilation window and the decompilation view. And there are also other views that will be provided in Mosra, like the control flow graph or the listing view. And this is how we handle the legacy EVM decompilation. But in EOF, we no longer need, in EOF, we no longer need this one because we have co-F, the return F, and jump F. And we also do not need this one because we have the type section. And for handle the EOF bytecode, we further defined the slate definition for the newly added operation. Like this is co-F, for example. We're inspired by the x86 JMP operation, and this is how we define the co-F opcode. And after all the works, this is the final result for the function co-graph in Mosra. This is impossible for us to reconstruct this concise graph in legacy EVM contract because the program analysis was very difficult. But with the features in EOF, it becomes much more easier. And this is a very beautiful control flow analysis graph in each function. And this is also impossible in legacy EVM contract because we need to tackle with different patterns and there is no specific layout in the bytecode sequence. But with EOF, everything becomes more easier and possible, and we could develop even more powerful analyzers for the bytecode. So this is all my presentation today. I hope everyone attending this session learned something about Ethereum object format and the program analysis. And if you have any questions, you could send your question to this email or contact me on Twitter. And this is our tool. You can try it out and also contribute to our tool. All right, thank you for listening today.
Thank you, Louis. Great talk. So we have 2 minutes, so probably one question. Any question? Okay, yeah. This gentleman. Waiting for the mic.
Hey, I really like the detailed examples you gave on the slides. I was wondering, with like the structure we get from EOF, if there's any assumptions we can make during execution time for any runtime optimizations?
That's a good question. So you mean based on EOF, whether we could do some optimization for the bytecode?
Yeah.
Yeah. I'm not very sure because most of our work focuses on the decompilation part of the bytecode. So I'm not very sure how the EOF will facilitate the runtime execution, but like we mentioned earlier, there is exchange or swap in, dupe in operations. It will significantly help with the stack arrangement in EVM, because in the past we need to use a lot of pop or swap operation to rearrange the stack element. But now we could simply use exchange, or we could use swap in, just one operation to place the item on a desired position. Yes.
Thank you.
Thank you for your question.
Okay, so no more questions. If you have more questions, you can reach out to Louis directly. So thank you for the thorough explanation about EOF. So thanks again to Louis.
Okay, thank you.